All right, now that we know what K means and what its values mean, we're going to do some calculations using K. There are a number of options, and we need to realize whether or not we are actually calculating K itself or whether or not we are using K, because it's going to give us different options. So in this case, we have been given K, and we're trying to calculate a partial pressure. And we have been given entirely equilibrium mixtures or equilibrium amounts in this reaction. We know that K, and this is going to be a K sub P because these are pressures, are going to equal the pressure of PCl3, one of the products, multiplied by the pressure of chlorine, divided by the pressure of PCl5. We're given the K value of equal to 0.497, and that's going to be equal to the pressure of PCl5, which is 0.860, multiplied by the pressure of chlorine, which is what we're solving for, divided by the pressure of PCl3, which is 0.350. And because these are all at equilibrium, and that is very important, that these are all at equilibrium, we can simply plug our numbers into our expression. Remember, this is our expression for K, and we can solve for the pressure of chlorine. And when we do that, we're going to find that the pressure of chlorine is 1.22. Our units for pressure in our equilibrium are always going to be atmospheres. So let's make sure that we have a procedure. So step one, we're going to write the balanced reaction. Now we have to write the balanced reaction because if we don't have a balanced reaction, we can't write the equilibrium expression. So here in this chapter, our balanced reaction is always going to be given, but in the next two chapters, they're not. So we just need to remind ourselves to write the balanced reaction. We are then going to write our equilibrium expression, meaning we're going to write that K is equal to the concentrations of products over the reactions. Also, this can always be pressures. We know we're going to raise those values to their stoichiometric coefficients. We're going to take a look and see if we have initial concentrations. If we do, we're going to look at K to see what the direction of the shift is. Very frequently, we are going to be in an empty container. And if we put some initial reactants into an empty container, then our reaction is going to go always towards our products. We're going to apply our changes, and we're going to look back in, and we're going to calculate K or calculate some equilibrium value. So again, step one, balanced reaction, write your equilibrium expression, and then figure out what's going to go on from there. So we have a technique or a tool that we use, and the tool that we use is an ICE table. ICE stands for initial, change, and equilibrium. So we are going to write our balanced reaction. So let's say that we have AA plus BB goes into CC, and we have this at equilibrium. We're going to start out with our initial, we're going to have our change, and we are going to have our equilibrium. Now we're going to take advantage of the fact that because we know our balanced reaction, we know what our change would be. So if we have an initial amount of these guys, we know that our A is going to go down by some value of minus A. And again, this is going to assume zero products. And if we have an unknown amount, it would be minus AX. If our B is also going to go down, and it should be, it's going to go down by some value BX, and C is going to go up by some value CX. Why? Because we know for every A of these, we're going to use B of these values. At equilibrium, we're going to solve something. So again, we're going to write our balanced reaction. We're going to write our equilibrium expression. If we know K, we're going to solve for X, and we're going to go from there. So here we're looking at a value for K. So we're at some new temperature than we had before, and we're given some initial values. And again, our chart is going to be here on the left side are going to be our reactants. And I have color-coded these, try to make it a little bit different. These are our products. We're being told that this is in an empty flask, so we are going to have 0 of our products. Our relationship here is 1 to 1 to 1. So for every 1 PCl5, going to go down by 1. How do we know it goes down? Because our products are 0. Our PCl3 is going to go up by some value of 1x, and this is going to also go up by some value of 1x. Now, we've been given one more piece of information because right now we have one equation and two unknowns. We don't know what our equilibrium values are or what our K is. So we better know something else, and that is, in this case, the equilibrium concentration of PCl5. Well, if PCl5 started at 0.5, went down by some value, and is now 0.1, then clearly the amount it went down by is 0.4. And so our X value here is going to equal 0.4. Why? Because 0.5 minus 0.4 is going to equal a value of 0.1. All right, so let's write this down. We know that our K is going to equal the pressure of PCl3 times the pressure of Cl2 over the pressure of PCl5. And we have our reaction of PCl5 is going to go into PCl3 plus Cl2. And we're going to have our table. And our table, again, is initial change equilibrium. And that's going to be our ice. We started here with a 0.5. We ended up at a 0.1. So our change is minus 0.4. If our PCl3 and Cl2 started out to be 0, if this went down by 0.4, our PCl5 has to go up, or PCl3, excuse me, has to go up by 0.4, and chlorine has to go up by 0.4. Note, if one side goes down, the other side has to go up, such that at equilibrium now we have 0.4, 0.4, and 0.1 of the PCl5. We can plug this in and solve for K now, because we're going to take our equilibrium values and plug it straight into our K, giving us 0.4 times 0.4 over 0.1, and when we solve for our K value, we're going to get K is equal to 1.6. K is a unitless, and we're going to leave it right there. All right, so let's look at one where our relationship is not 1 to 1 to 1. In this case, we have 3 to 1 to 2. And this is important because if we start out with a certain amount of our reactants, and in this case, we're starting out with 2 moles of hydrogen in a 2-liter flask, if we're given moles and volume, so we're in units of molarity, so we have to remember that our K sub C is always going to be in molarity. If we have a K sub P, it's always going to be in atmospheres. So we are going to have to take here 2 moles divided by 2 liters, and we're going to get 1 molar. So again, molar here. Our nitrogen concentration is the same, and it's also 1 molar. The flask is empty, so we have 0 ammonia. So what are we going to do with our ratio? Well, we have 3 hydrogens to 1 nitrogen for every 2 ammonias. So we know that if our changes or our hydrogen is going to change, it is going to go down 3 times as much as nitrogen is. So our change is going to be minus, and again, it's minus because we're going to have to lose reactants and make products. It's going to be 3 from that 3 value, so our change is minus 3x. Our nitrogen is minus x again, minus because it's reactant, and our products, because we have a 2 here, are plus 2x. With all of that in mind, now we realize we have more information. We have information that tells us that at equilibrium, the concentration of ammonia is equal to 0.25 molar. So if we started at 0 and we ended up at 0.25, this has to go up by 0.25. We know that 0.25 is equal to 2x, which tells us that x is equal to 0.125. So now we can plug this in and we can finish our table up. So let's plug our numbers in. Our ammonia is going to go up by 0.25. We know that 0.25 is equal to 2x, so x is equal to 0.125. Our nitrogen is going to go down by x. Our hydrogen is going to go down by 3x, but we know what the value of x is, so these are just numbers. So our x here is going to be minus 0.125. Minusing our 3x is going to be minus 0.375. And when we get to our equilibrium, we really are going to take initial, which will be 1. We will apply the change. So if there's a negative sign here, we're just going to keep and we're going to write it down. And so it's going to be minus 0.375, and at equilibrium, we're going to get 0.625. This is going to be 1 minus 0.125, and this is going to give us a value of 0.875, and we already know what ammonia is, and we know what our K is. Our K is going to equal the concentration of ammonia squared, the 2, times divided by the concentration of nitrogen times the concentration of hydrogen cubed. So plug it in. 0.25 squared divided by 0.625 cubed times 0.875. We have our values at equilibrium. We're going to take again and plug this into our K, and we're going to find out that our K here has a numerical value of 0.29. So we're going to continue some other options. So again, we're going to verify that we have a balanced reaction, and we do. We are going to write the expression for K. Our K is going to equal, and we look at these and realize that we have concentrations. So it's going to be the concentration of HF squared divided by the concentration of hydrogen times the concentration of fluorine. This has a numerical value of 1 times 10 squared, or 100. And in order to solve for something, we have to find these equilibrium values. So let's start this out and write it down. We have 1 mole of H2 in a 500 ml flask. So if we have 1 divided by 0.5 liters, we're going to have 2 molar. Again, our units have to be molar if we're using a K sub C. Fluorine is the same, and it's 2. Our flask is empty, so unless we're given some values, so notice we are not given an HF, and if we're not given an HF, we are going to assume that we have 0. We know our reaction is going to have to shift towards products because we have a 0, and we're going to look at our changes. Now we don't have any other information. We have K, and we have our initial, so our changes are going to be X. Hydrogen and fluorine are 1 to 1, so this is going to be minus X and minus X. HF is going to be up by a value of 2, so this is plus X. Realize that the reactants are going to go down and the products are going to go up. Again, why? Because we have no products. And so at equilibrium, we're going to have 2 minus X, 2 minus X, and 2X. What do? We take these values right here and we plug them into our K. All right, so let's go back and look at this. We know we have a value of 2, 2, and 0. Minus X plus 2X. So this is going to be 2 minus X, 2 minus X, and 2X. Our K is 100, and that is going to equal the concentration of HF squared over hydrogen times fluorine. And we're going to plug our equilibrium values in here. Now notice I put in a second row here so that I can figure out a nice clean place to put my answers. So if we plug this in, we're going to get 2x squared over 2 minus x times 2 minus x. We look at this, we can simplify this because we have 100 is equal to the quantity 2x squared over 2 minus x. The quantity squared, if we square root this whole mess, we are going to get 10 is equal to 2x over 2 minus x. And when we finish our rearrangement and solving for our answer, we are going to get our x is equal to 1.67. And when we have this, we can plug this back in. It tells us that hydrogen is going to have a concentration of 2 minus 1.67. So we're going to have a value here of 0.33. Our fluorine is going to be the same, and that's going to be 0.33. And our equilibrium value of HF is going to be 2 times 1.67, and that's going to equal a value of 3.33. And these are our final answers and our final concentrations of hydrogen, fluorine, and HF. All right, we've got a couple of more options. If we can't simplify, we may end up being stuck with the quadratic or hoping that we can make some approximations. And this is our favorite approximation because we do this a lot. And we do this when K is small. We know that if K is small, and we say as K is small, it's going to have to be less than about 10 to the fourth, minus 4, in order for this to work. So a nice small k, what does this mean? It means that we have very few products. Okay, we know it has very few products, but more importantly than that, we also mean it's got a lot of reactants, which are also going to tell us that very few reactants go away. How does that help? This is going to allow us to approximate and set our x equal to 0. Now, it won't be all x's because then we won't have a math problem. It's going to be the x's compared to some original reactant concentration. So let's write some stuff down. We're going to start out with 0.8 molar of nitrogen, zero point 0.8 moles in 1 liter, zero point 0.2 molar of O2, and 0 of the NO. This is going to go down by x, going to go down by x, up by 2x, such that at equilibrium we have 0.8 minus x, 0.2 minus x, and 2x. Now note, we try to keep our math simple so we don't worry about our sig figs as we're doing these. We worry about our sig figs at the end. So let's consider the math. So again, here we have 0.8 minus x, 0.2 minus x, and 2x. And we know that our K is going to equal concentration of NO squared over nitrogen times oxygen. Our value of NO, of K, is given as 1.0 times 10 to the minus 5. And that's going to equal 2x squared over 0.8 minus x times 0.2 minus x. All right, so how does this value of K help? Well, if K is small, then very few reactants go away. This tells us that if we consider 0.8 minus x, this x is going to be very small. When K is small, x with respect to the initial will be very small. How does that help? Well, that helps because that means that 0.8 minus x is about the same as 0.8. So if we rewrite this and we get 1 times 10 to the minus 5 is equal to squaring 2x, that would give me 4x squared, divided by 0.8 minus x times 0.2 minus x. Because this 0.8 minus x is about equal to 0.8. This x with respect to the initial is small. I'm going to set these two x's equal to 0. Obviously, I can't set the numerator 1 equal to 0 because then I haven't got a math problem. So I have 1 times 10 to the minus 5 is equal to 4x squared over 0.8 times 0.2. Rearranging, doing the multiplication and division, and taking the square root, I'm going to get a value of x equal to 0.00063. So, first of all, is it going to be a good approximation? Well, the answer is yes, because 0.8 minus 0.00063 is going to be equal to about 0.8. Okay, our approximation is good, which means our concentration of O2 is also going to be about the initial, and our concentration of the NO is going to equal 2 times 0.00063, and that's going to equal a concentration of 0.0013. So what's the takeaway? When K is small, and when we mean small, less than about 10 to the minus 4, we can set the change here, our x with respect to the initial, equal to 0. So we will be setting these changes here equal to 0. What does that do? That dramatically simplifies our math, because the last thing we want to do is the next step, which is the quadratic. All right, so here we are, and we're stuck. Our k is not very small. Our k is equal to 3, so we can't make any approximations. We have a simple value of 0.5 of NO placed in an empty flask, and it's going to dissociate, and evacuated is the same as empty, and excuse me, it's going to react and make an N2O2. You know our equilibrium expression. Our K is going to equal the pressure, and this is a case of P, is going to equal the pressure of N2O2 over the pressure of NO squared, and this is simply equal to 3. Our job is to find the pressures at equilibrium. We know our change here is going to be minus x and plus 2x. At equilibrium, 0.5 minus x and 2x. And we are going to get that 3 is going to equal 2x over 0.5 minus x, the quantity squared. We can't make any approximation, so we're going to have to plug this into the quadratic. All right, so again, 3 is equal to x over 0.5 minus 2x squared. So let's just make sure we remember how to do our math. So this is going to be 3 times 0.5 minus 2x multiplied by 0.5 minus 2x is equal to x. If I do this stuff in the middle first, I'm going to get 3 multiplied by 0.25 minus 2x plus 4x squared is equal to x. If I multiply through by the 3, I'm going to get 0.75 minus 6x plus 12x squared is equal to x. If I put the x on the other side, I'm going to get 12x squared minus 7x plus 0.75 is equal to 0. If you haven't got the quadratic plugged into your calculator, you're going to have to remember that negative b plus or minus the square root of b squared minus 4ac all over 2a is going to equal x, where this comes from ax squared plus bx plus c is equal to 0. Plugging this in, you're going to find two values for x corresponding to plus and minus. Only one of these is going to be reasonable. When I plugged this in, I got x was 0.4 and I got x was equal to 0.44. So which one of these is going to work? Well, note that the concentration here of the NO is going to equal 0.5 minus 2x. If I use the value of 0.44, I'm going to lose more than I started with to begin with, which means that that value will not work, and we're going to cross it off. So the only one that can work is 0.14, and the concentration of NO is going to equal 0.5 minus 2 times 0.14, and that is going to equal 0.218. The concentration of N2O2 is simply equal to X, and that is equal to a concentration of 0.14. All right, so those are our final values. I think these are actually pressures, not concentrations, but you know what I mean.